Last video I was able to solve the Fibonacci sequence here, and I found that this was the solution here, the closed form solution, and it involves the golden ratio and the golden ratio conjugate. In the video before last, I looked at, before solving it, I looked at some of the different things that you can notice about the Fibonacci sequence, and so I want to come back to those now that I have this closed form solution and look at why those things were. So the first thing you can notice is if you look at a given Fibonacci number and you divide by the previous Fibonacci number, that ratio you get seems to be approaching the golden ratio. And the other thing that I noticed was that if you look at that ratio for each term, here it's under, here it's over, 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 talking about with relation to the golden ratio. So we have some sort of oscillation going on in the solution. So the thing to notice here is if this were an equal sign, if you had Fn plus 1 over Fn is equal to the golden ratio, your solution essentially would just be this first part here. This constant would depend on your initial value, but essentially you're just going to get a golden ratio to the n. So this new term here, this is what's of interest. And if you look at it, this is golden ratio conjugate. If you look at the golden ratio conjugate, there's something, there's a couple properties it has. It's between -1 and 0. And so what that means, with it being the base of an exponential function, is two things. Since it's negative, that means that it's going to be oscillating between positive and negative. If n is even, then golden ratio conjugate to the n is going to be a positive number. If it's odd, it's going to be a negative number. And so that explains why you have this oscillation here between these ratios. The other thing is, since it's less in magnitude than 1, that means that it's as n increases, the golden ratio conjugate to the n decreases. It's a decaying exponential function. So that can explain this other behavior over here, because if you look at the limit as n approaches infinity of Fn plus 1 over Fn, what you'll find is, I guess I'll just write it out. So these are going to cancel out first of all, and on the top you're just going to have this. And on the bottom you have this. So as n approaches infinity, these are going to cancel out, and so you're just going to be left with golden ratio of n plus 1 over golden ratio to the n, and so then the golden ratio to the n cancels out, and then you see that this is just going to end up being golden ratio as n approaches infinity. So you may have noticed that I have this other column over here that's kind of unexplained, and I also have this picture of a plant. So the reason for that is a lot of time when people are talking about the golden ratio, they talk about things in nature, because the Fibonacci numbers come up a lot in nature. They come up, and if you look at plants, oftentimes the amount of leaves they have is a Fibonacci number. And if you look at bananas, so they say the amount of sides is a Fibonacci number, but realistically I found that there's actually a lot of four-sided bananas out there, and 4 is not a Fibonacci number. So I don't know. Also, I don't know, I'm kind of skeptical about the whole like saying everything must be a Fibonacci number, because if you look at them, they're pretty densely packed together here for the small amounts. Like, I went to the store the other day and they had like beef jerky on the shelf, and they had like the beef jerky packaged with like 8 in each one, but I don't think that's because it's a Fibonacci number. But I want to give an example of why this could be related to plants and stuff like that. So let's say I'm a plant and I have a certain amount of sides here, like 5. That's 5's good, but I'd rather have more because I'm a plant and that's what plants want. So if you look at the amount of leaves I have I'm just going to represent this by like a line segment here, and I'm going to call its length Ln for the amount of leaves. So in this case it would be 5, so I could do something like that. And so what I want to do is I want to increase this. So I'm going to add on a bit here, and this new total amount, I'm going to call that Ln plus 1. And so the question is, how do I want to choose what that Ln plus 1 is? Well, one way I could choose it is I could say I want the ratio between the new amount that I have and the current amount that I have. I want that to just be equal to the ratio of how much I have now and how much I'm going to add. So that would look something like this. This amount that I'm going to add, this would just be the new amount, Ln plus 1, minus the current amount. And so I showed before, well, it was more of a definition. This is just the golden ratio. And so if I take this equation right here, this is just the equation I was talking about before. This has a very easy solution. You can guess it. I showed it in, I think, the second video. So this thing has a solution. L of n is just going to be the initial L times golden ratio to the n. And so the only problem with this is if I have 5 leaves, then this is telling me if you want to look at Ln plus 1, that's just going to end up being golden ratio times 5 leaves, and golden ratio is not an integer, so the new amount I'm going to get is not an integer, and that's a problem because you have to have an integer amount of leaves. So what could be happening is you could just have a rounded version of that. And so what ends up happening is if you choose L0 to be 1 over root 5 and you look at the rounded version of Ln, you're going to just get the Fibonacci sequence. It's exactly equal. And if you look at why that is, that's just because this amount here, the only difference now in this equation Ln and Fn is just this term here. And this term is always going to be less in magnitude than 1/2. And so the rounded version of this is just going to give you this.